Let's take a look at the equations for the Doppler effect. Okay, what I have here is the sound source, which is at rest, and here's the observer, O, which is also at rest. This represents the observed frequency, and this represents the frequency of the source. If both the observer and the source are at rest, the observed frequency will be equal to the frequency of the source. I place the observer one wavelength of sound away from the source. Okay, so this crest, when it's emitted, the next crest will be emitted by the source when this crest reaches the observer. And of course it takes a time, tau, okay, the period, for the wave to travel from the source to the observer. Now let's say that the source is moving toward the observer. And let's say it travels a distance equal to d in a time tau. So in other words, in the time it takes this crest to reach the observer, here, it has reached the observer here, the source travels a distance d, at which time it emits the next crest. So you notice that we have a new wavelength, lambda prime, which we're going to calculate. Now the distance the source travels in the time equal to the period of the sound wave is given by the speed of the source multiplied by the period. That's just from the equation speed is distance over time. Okay, so let's write an expression for the new wavelength. The new wavelength here should be equal to the original wavelength when there was no relative motion between the source and the observer, minus the speed of the source multiplied by the period. This is the distance traveled by the source in a time tau. And I'm going to call this equation 1. Equation 2 is going to be this equation, which is also from the equation speed is equal to distance over time. The frequency of that the observer detects should be equal to the speed of sound, and I'm using the symbol V for that, divided by the new wavelength. Okay, so this observer here, when the observer is here and the source is approaching him, the frequency the observer will detect is given by this expression, and that I'm going to call equation 2. Keep in mind, by the way, that the speed of sound is relative to the air, which is considered to be stationary, so there's no wind here. Now I'm going to take equation 1 and I'm going to substitute it into equation 2. So I get that the observed frequency, when the source is moving, is equal to the speed of sound v divided by lambda wavelength minus the speed of the source times the time, the period of the wave. And this I'm going to call equation 3. Next, I'm going to write an expression for the speed of sound in terms of the frequency of the source. The speed of sound in terms of the frequency of the source would be equal to the wavelength of the sound wave times the frequency of the source. Okay, so if you look up here, you'll understand that, right? When the observer and the source are at rest relative to each other, the frequency of the source multiplied by this wavelength should be the speed of sound. When the source is moving, the speed of sound v then would be equal to the observed frequency times the new wavelength. Okay, now this equation I'm going to call equation 4. Equation 5 relates the period to the frequency. Isn't the period of the source frequency, the period of the wave emitted by the source, equal to 1 over the frequency of the source? And that I'm going to call equation 5. Now I'm going to take equation 4 and 5 and substitute them into equation 3. And in so doing, I get that the observed frequency is equal to the frequency of the source times the speed of sound divided by the speed of sound minus the speed of the source. Now this equation can be simplified to look as follows. And I'll put that right here. the frequency observed is equal to the frequency of the source divided by 1 minus the quotient, the speed of the source, over the speed of sound. You'll notice that if the source is traveling at the speed of sound, we get 0 in the denominator, which means that the observed frequency will be undefined. This is sometimes called the sonic boom. Let's next look at the case where the source is moving away from the observer. Okay, so going back up here, right here we have the source, here the observer. They're both at rest right now. The observed frequency is going to be equal to the source frequency. The wavelength is lambda, and the time is the period of the wave, the time it takes the crest to reach the observer. Okay, if you look at this diagram below here now, okay, now we have the source moving away from the observer. And the time it takes the source to go from here to here, we're going to call a period. If you take that period and multiply it by the speed of the source, you will get this distance here. Now, the crest that was originally sent out by the source, right here, has reached the observer when the source that's moving away sends out the next crest a time equal to the period of the wave later. So we can write an expression now for the new wavelength. The new wavelength is equal to the original wavelength plus this additional distance here, d, which is given by the speed of source times the period. And this I'm going to call equation 1. Equation 2 will be this equation again. The observed frequency is equal to the speed of sound divided by the new wavelength. That I'm going to call equation 2. I'm going to substitute equation 1 into 2 as before. Observed frequency is equal to the speed of sound divided by the original wavelength plus the speed of the source multiplied by the time, which is the period. And that I'm going to call equation 3. I'm next going to use this equation as before. The speed of sound is equal to the original wavelength times the frequency of the source. That's equation 4. And the equation that relates the period to the frequency of the source. The period is equal to 1 over the frequency of the source, and that's equation 5. Now I'm going to come take 4 and 5, and I'm going to insert them into 3. And I'll do that right here. And if I do that, I get that the observed frequency is equal to the frequency of the source times the speed of sound divided by the speed of sound plus the speed of the source. This is algebraically equivalent to the following. So let me erase this. Actually, let me erase this and rewrite it. So this equation gives the frequency observed if the source is moving away from the observer. It's equal to the frequency of the source divided by 1 plus the speed of the source divided by the speed of sound. What we're going to take a look at now is the case where the source is at rest and the observer is moving toward the source. And then we'll take a look at the case where the source is at rest and the observer is moving away from the source. This is different than the previous two derivations because here the waves are not going to be compressed. The source isn't moving. So the waves will have the same wavelength. The wavelength will not change. So if the observer is moving toward the source, and let's say that in a time delta t, some time delta t, this isn't necessarily the period of a wave or anything like that, it's just an ordinary time, it travels a distance d, and that's found by taking the speed of the observer and multiplying it by how long the trip is. So imagine that this is a helicopter and you're in it and you're flying over the ocean. Okay, so these are ocean waves. Okay, and when you fly over the ocean, okay, what will happen is you're going to see a certain number of wavelengths per unit of time. And the way you would figure that out is by taking the distance you travel, which is VO times delta t, dividing it by the actual wavelength, and then dividing that by time. And what that will give you is the additional number of wavelengths that you encounter per unit of time. And that's a frequency. And you would have to add that to the frequency of the source, okay, which is the frequency of the waves you would detect anyway if you weren't moving. So the observed frequency then, when you're moving toward the source of sound, would be equal to the frequency of the source plus the distance you travel in a certain amount of time, VO delta t, divided by the actual wavelength, which remember is a constant, divided by the time. Okay, and this quantity in the numerator again represents the additional number of wavelengths that you encounter during your motion, or if you're a helicopter, during the fly over. If you divide that by the time over which this encounter occurs, you will get the new or the additional frequency that you have to add to the frequency of the source. Okay, so this term here reduces to VO over lambda. And this can be written as Fs times the quantity 1 plus VO divided by Fs lambda. And now what I'm going to do is I'm going to take the equation for the speed of a wave, the speed of sound, in terms of the frequency of the source and the wavelength, call that equation 2, and substitute that into 1, and we get our equation for predicting the observed frequency when the observer is moving toward the source. And that's equal to the frequency of the source multiplied by 1 plus the speed of the observer over the speed of sound. Now let's take a look at the case where the observer is moving away from the source. So, in a certain time t, the observer moves a distance d, which is given by the speed of the observer multiplied by the time of the story. So the observed frequency then of this observer moving away from the source would again be equal to the frequency of the source, and that's what the observer would hear if the observer weren't moving away. But then we have to subtract from that the frequency that it will miss by traveling in the direction of the waves. It's a little trickier to understand, and I'll help you better understand this in a moment. So I'm going to take Fs and subtract from it this distance, which is VO delta t, divided by the wavelength, divided by the time of the story. So up here, this represents the missed number of wavelengths encountered, and this represents the time over which the encounter occurs. So to understand this a little bit better, imagine that the observer is traveling at the speed of sound. So that would make this quantity Vs, and then we would end up with Vs divided by lambda, delta t's cancel. But isn't Vs over lambda equal to the frequency of the source? So in other words, the observed frequency would be 0. If you're traveling with the waves, you will not detect any frequency. That is, if you're traveling with the waves at the speed of the waves, you will not detect any frequency. So continuing here, we get then that the observed frequency is equal to the frequency of the source minus the speed of the observer divided by the wavelength, which can be rewritten as the frequency of the source multiplied by 1 minus the speed of the observer divided by the speed of sound. Okay, so this equation predicts the observed frequency when the observer is moving away from the source. And again, you can see here that if the observer is traveling at the speed of sound, this term goes to 0, take 0 times the frequency of the source, and you get a 0 observed frequency.
I strike the tuning fork, and the oscillating prongs set up a sound wave. Longitudinal spherical waves are created, where the speed is equal to the wavelength times the frequency. What if the source of the sound moves? Hello, a passenger train is approaching this railroad crossing. Listen to its horn. The change in pitch you just experienced is called the Doppler effect. It happens when a sound source moves relative to you. Did you see how the waves were compressed in the front? Wavelength times frequency is equal to the speed of sound, which, like light, is a constant in any given medium. In front of the source, there must be a larger frequency since the wavelength is smaller. Question: what do you hear if you're moving with the source? No Doppler effect if you're moving with the source of sound.